Yeah, thank you so much, and good morning for everyone. I'm Victor Mayta from University of Wisconsin, and I would like to start with many thanks to the organizer for inviting me for this important moist convection dynamics of monsoon workshop. And today I will present for you moist thermodynamics of tropical waves, which is a work in a collaboration with a PI of my group, Professor Angela Dames Correlisa, and the postdoc in my group, Chavez. Okay, I'm going to start off showing this animation of brightness temperature, which is commonly used as a proxy of convection. When you first look at this animation, you probably see that the convective organization of the tropics are apparently chaotic. But this is because tropics contain a diversity of weather systems with a wide variety on spatial and temporal time scales. I show it in this space-time spectrum of the brightness temperature, the same used in this animation. There are, of course, a family of tropical waves, some of them propagating eastward, like Kelvin waves, the Madden-Julian oscillation, and there are other waves that propagate in the opposite direction, like equatorial Rossby wave, tropical depression system, the westward inertial gravity waves, and most of the time, all of these waves are acting in the same time. This is why the tropics looks like really disorganized. But if you extract the information, for instance, of these disturbances, in this case, the Madden-Julian oscillation, and plot together here in this animation, you will see that a large portion of the convection is fairly well organized by this Madden-Julian oscillation, which is propagating eastward, impacted precipitation, not just over the tropical region, it also impacting precipitation above the world. If you plot, for instance, the Kelvin wave, you can also see it's plotted here in our red curves. You will see that Kelvin waves also propagating in the same direction of the Madden-Julian oscillation, but in this case, these Kelvin waves propagate really faster compared to the Madden-Julian oscillation. If you move away from the equator, you can also see a diversity of tropical depression system. It's called, for instance, easterly waves over the Western Pacific. And you can also see this monsoon low pressure system over the Indian region, which is in fact played a really important role in organizing convection over the Indian Ocean, over the Indian region. So these waves can be classified in different ways. For instance, you can classify the waves that propagate, for instance, eastward. You can have like Kelvin waves, MGO propagating in that direction. You can have waves, for instance, that propagate in the opposite direction, like Rossby wave, TD, and westward inertial gravity waves. You can also classify these waves, this family of waves, according to this horizontal extension. You can have, for instance, large-scale disturbances like Madden-Julian oscillation, or you can have, for instance, smaller-scale disturbances or synoptic scales like the two-day waves or westward inertial gravity waves. But in this talk, I will try to classify these disturbances in two main groups. In this case, according to the propagation characteristics. So we will try to divide all the disturbances that mentioned previously in two main groups. The first one, we classify the fast propagating disturbances. For instance, the mixed Rossby gravity waves represent this group. This is a mixed Rossby gravity waves over the Western Pacific that in fact play a big role in organizing convection over this region. So what characterizes these fast propagation disturbances? First of all, short time scale, which is an important characteristic of these disturbances. Fast propagation, in this case, for instance, this wave propagate at about 25 meters per second over this domain. Another one is the temperature play an important role in the thermodynamics of these disturbances. In the other group, we have the slow propagation disturbances. And a clear example for that, for instance, represent the equatorial Rossby waves. This is the equatorial Rossby waves over the Indian Ocean, and you will see these gyres that closely resemble to the theoretical Rossby waves. So what characterizes these slow propagation wave disturbances? So in this case, these waves is characterized to have long time scale, slow propagation. So for instance, compared to this wave, this Rossby wave over this domain basically propagate at about 5 meters per second. And the other feature is that moisture, in this case, play a central role in the thermodynamic of these disturbances. As you may notice here, I highlighted two important features in these slow propagating groups. The first one, the slow propagation, and the other one, moisture playing a central role in the thermodynamic of this disturbance. So why I mentioned that? Because convective couple equatorial waves, as we showed previously, are often viewed as the extension of the dry waves with a reduced equivalent depths to represent moist convection. So the question is if this theory accounts for all disturbances observed in the tropical region. And maybe the answer is not. And a clear example for that is, for instance, doesn't exist a dispersion curve for the Madden-Julian oscillation. We don't have a dispersion curve, for instance, for the TD-like disturbances. But the other wave, Kelvin wave, for instance, can be predicted by the theory. And you can also say, oh, of course, Rossby waves, the equatorial Rossby waves can also be predicted by the dry theory. But it's not totally correct to assume that these equatorial Rossby waves, the observed equatorial Rossby waves, correspond to this equatorial Rossby wave from the dry Chavez theory, just because it follows these dispersion curves. So the assumption that is made in this dry theory doesn't align with the observed characteristics, the thermodynamic characteristics, which is, in fact, is needed a new theory to understand these slow propagation disturbances. Of course, if you want to understand this kind of disturbances, slow propagation disturbances, you need to include a moisture as a prognostic equation in your set of equations. And doing that, you will have like a dispersion curve for these disturbances. Of course, the dispersion curve is a little bit complex compared to the dry theory, but at least you can have, for instance, the dispersion curves that explain the spectrum associated to the tropical depression system. Okay, let's go back to the tropics. So we can say there are two main features that characterize the tropical region. The first of all is the weak temperature gradient, which is observed over this domain. This is temperature at 700 hectopascal. Show it in this 25 north, 25 south domain. You can say temperature over the tropic is pretty homogeneous and changes little in time and space. The other main feature is that there is a large moisture fluctuation over the tropics that in fact drives and shapes the wave activity over this domain. These two main features, weak temperature gradient over the tropics and large moisture fluctuation over the tropical domain, give us one important consequence. In this case, is the existence of so-called moisture modes. If you never heard about this term, moisture modes, we can easily define as a type of tropical motion where the weather vapor basically plays a central role in its dynamics and thermodynamics. And these waves don't exist in the dry theory. Okay, after this quick introduction, we can basically try to answer the following question in this talk. The first question is, when trying to discover if moisture mode exists or not. If moisture mode exists, where are they most common? The third question is, what process control the growth and propagation of these moisture modes? And finally, when trying to explore the main role of these moisture modes in the main circulation over the tropics. To answer this question, I basically used clouds brightness temperature that showed it in the previous animation, and we used era 5 reanalysis data to discuss the the structure and the thermodynamics associated to these disturbances. Okay, what exactly constitute moisture modes, or how I can identify moisture modes? Previous studies, for instance, ACME 2021 and Mayta 2022, proposed some criteria to identify moisture modes. So they basically proposed 3 criteria. The first criteria basically says that to wave to be classified as moisture mode, a moisture anomalies must exhibit a high coherence with precipitation anomalies. So this relation should be true to say your disturbances basically satisfy the condition to be considered a moisture mode. The second condition basically says that to be classified a moisture mode, the WTG balance, the weak temperature gradient balance, should be true at the leading order, or this balance should be true if you are trying to classify your disturbances. And the third criterion basically say that thermodynamic variation in the mode must be dominated by moisture. So if you, for instance, calculate the moist static energy, so the moist static energy calculation basically should be explained by the moisture variation. So if you apply this criteria, so it's pretty easy. So it's pretty easy to demonstrate all these criteria in observation, in analysis, even in modeling outputs. We basically proposed that the TD-like disturbances and the Rossby waves are the only disturbances that satisfy all criteria to be considered moisture mode. The other waves will show some characteristic of moisture modes or can be classified as another type of disturbances. Another criteria that can be used to classify the different disturbances over the tropics is the so-called N mode. N mode is a no-dimensional parameter that basically measures the relative contribution of temperature and moisture in the evolution of the most enthalpy. If this value, N mode, is less than 1, we basically can say moisture governs the thermodynamic of this disturbance. So this N mode calculation have like a most strict definition, which includes like other trends like the phase speed propagation, the time scale of the disturbances, the convective moisture adjustment time scale. But if you do a scale analysis, the N mode can be simplified as this term. Basically, the phase speed propagation determine if your disturbances can be classified as a moisture mode or is as another kind of disturbances. So this N mode you can plot together here with the brightness temperature spectrum, which is shown here as a contour. And the shade basically is the N mode plotted as a wave number and frequency. So everything that's in blue in this diagram correspond to the moisture mode. The white region means the mixed region, or basically where moisture and temperature play the similar role. And the yellow one corresponds to the gravity wave region. So if you go here, you will see that the spectrum of the Quattro Rossby wave and TD basically fall into the blue region, which means these disturbances, according to this criteria, can be classified as a moisture mode. Colin wave is a clear example that when you do this calculation, this term or this wave can be classified as a mixed system, or for these Kelvin waves, temperature and moisture playing basically the same role in the thermodynamic of these disturbances. You can also ask, what about MGO picture? You can say, what about MGO? MGO is a moisture mode or not? So in this figure, I'm showing again the N mode variation across the whole tropical domain. So as mentioned in the previous slide, this N mode can be estimated by this, after doing a scale analysis you can estimate, or is basically dominated at the phase speed propagation. This MQ, this MQ, this MQ is basically Rowley to 0.1, and this phase speed, of course, can be calculated for the disturbances. Over the Indian Ocean region, over here, the wave, for instance, propagate from 3 to 5 meters per second. And if you consider, for instance, a phase speed of 4 meters per second and plug in this equation, you will get a value of N mode of about 0.1 N mode, which means the MGO, according to this N mode, can be classified as moisture mode over the Indian Ocean region. But outside the Indian Ocean region, the MGO, for instance, over the maritime continent and Western Pacific, the wave propagates, for instance, from 5 to 10 meters per second. And if you go outside the warm pole over the cool pole, the wave can propagate faster to 10 meters per second. So if you use this value, 10 meters per second, and plug it in this equation, you will get a value of N mode Rowley to 1, which means the wave basically behaves as a mixed system. So outside the Indian Ocean, the Madden-Julian oscillation can be better classified as a mixed system. So temperature variation, moisture variation play an important role in the thermodynamic of the wave. So just TD and Rossby waves can be classified as a moisture mode in the whole tropical domain. And the Madden-Julian oscillation is a moisture mode, but just in a specific region. Okay, moisture mode exists. TD disturbances and equatorial Rossby waves are the only waves that can be considered as a moisture mode. And now the question is where these moisture modes are most common. To answer this question, I'm showing here in contours and the total column water vapor, and the shading basically correspond to the wave activity, is the variance of the wave activity, basically showing where these waves are more active. This first one is for the TD-like disturbances, and the second one is for the equatorial Rossby wave, which is the other moisture mode in the whole tropical domain. If you go here, for instance, for the TD-like disturbances or easterly waves over the Atlantic region, you will see that the maximum activity is basically located where the moisture gradient is stronger, not where the maximum column moisture is observed. So if you go, for instance, over the Western Pacific, the same happens. So the wave activity, the easterly waves over the Western Pacific is basically more active where the moisture gradient is maximum. It's not active over here. Here is, of course, the maximum column moisture. So the wave is basically acting over this region. So the same happened, for instance, for the equatorial Rossby waves. You will see the darkest color is observed over the region where the maximum gradient is observed. This is an important characteristic of this disturbance. They are not more active where the column moisture is maximum. Okay, the next question is what process control the evolution of this moisture mode? So to understand moisture mode, we can use the column MSC budget. I don't know if most of you are familiar with this equation, but basically the moisture evolution in the system can be understood by using, for instance, the horizontal vection of moisture, the radiative heating, and fluxes in the system. And this is, of course, is proportional to the evolution of precipitation into that system. So we can use this equation to understand how precipitation or how moisture is evolving into the system. Okay, let's start with the contribution to the wave propagation. Well, in this figure, each bar basically represents how much each term contributes with the propagation of our moisture modes. Well, in this case, the bar represents well, here the red circle means the maximum convection over the region of analysis, and this one represents 2 days previous the maximum convection at the point, and two days plus to the maximum convection over this region. So this is basically represent how the wave evolves over the system, how the different terms are contributing with the wave evolution of the system. So again, there are many terms here, but I'm trying to highlight here the most important terms that contribute, for instance, with the westward propagation of this moisture mode. You can see that these terms are, of course, contribute almost with 100% of the evolution of this wave. And this case is the horizontal moisture advection. So we can say that moisture modes propagates due to the horizontal advection of the trade wind. So this one, the U bar, represent the main flow. This term is also important because the wave is not just have like a zonal propagation. For instance, TD have like some propagation towards the north or depends toward the south. So this is why these terms are also important for these disturbances. So in this case, it's for the TD disturbances, but it's basically the same observed in the Rossby waves. Okay, let's move to the mechanisms that contribute with the growth of these waves. So the bars again is showing which process control with the amplification of the wave or the decay of the wave. So positive value mean contribution to the growth, and negative values means the contribution to the decay of the wave. From 2 days before the maximum convection at the base point and 2 days after to the convection at the base point. This is basically the wave evolution. So again, there are many terms here because we decompose the horizontal advection and vertical advection. But here, I'm trying to highlight the most important terms. Here, I will start, for instance, for this radiated heating, which in fact is one of the most important mechanisms that contribute with the amplification of the wave. So the reason why this term contributes a lot with amplification of the wave is because the upper level clouds that basically act as a blanket, which is amplifying, which is important moisture into the system. This mechanism is basically balanced by this other term, the vertical advection of main moisture. And this term you can understand as a large-scale clouds in the system with condensation and precipitation, which in fact is basically drying the system. But the most important thing here is that these two processes are basically balanced during the wave evolution. So they're trying to cancel during the wave evolution. And the terms that really explained the wave evolution in this case is the horizontal moisture advection. So you can see this one closely resembles what is shown here, the horizontal moisture advection. So maybe you can say, oh, this is super complicated. You show it many terms, but we can simplify the budget equation as shown here. So we can say that moisture evolution in the system can be explained by the horizontal advection, and the remaining terms in the budget equation we can just call the column processes. And when we plot these terms here, and this you can see this is the convective evolution associated to the tropical depression system. And this one and the dashed line represent the moisture evolution in the system, and the green line represent the horizontal advection, and the column processes is plotted here as a gray line. As you can see, the moisture evolution in the system is basically explained by this horizontal advection. The column processes is basically close zero during the wave evolution that we show in the previous animation. I'm not saying that column process is not important. I'm just trying to say the column processes are balanced during the wave evolution. And that really explain the wave evolution in this case is the horizontal moisture advection. But in this case, this is for the tropical depression system. But the question now is what happened for the other disturbances? In this figure, for instance, I'm showing the ratio between the horizontal advection and the tendency of moisture for the different waves. So for the TD, for instance, 1-to-1 relation is observed, which means this 2-1 is true for the TD waves. So similar behavior is observed for the Quattro-Rossby wave, which also means the horizontal advection also organizes moisture for these disturbances. The MGO is the other disturbances that can be considered that the horizontal advection actually play an important role in organizing moisture into the system. So the other system basically is not observed. So we can say that our moisture mode, TD, Rossby waves, and TD, and MGO is basically driven by the same processes. The horizontal advection play an important role in organizing this system. Okay, our next question is, what are the moisture modes are doing? What is the main role in the circulation of this wave? So if this term contribute or acts to amplify the column moisture into the system, as observed in the previous slide, imply that the moisture modes basically flux moisture polarward. So I show it in this figure. So contours here, for instance, represent the main total column in the tropical domain. The shading represent the TD wave activity over this region, and the arrow represent the eddy moisture fluxes. As you can see, for instance, here we have the African easterly waves or easterly waves of the Atlantic region, which in fact I show it with by this arrow. This one is exporting motion through the north. If you go to the Eastern Pacific, you will see that when this wave is active, are also exporting moisture through the south, through the north. The same happened over the Western Pacific. When this wave is active, are exporting moisture through the poles. So this is perhaps the most important role in the circulation doing by these waves. What about MGO? MGO is a little bit more complicated. Well, if you do the same analysis, you can also see a polarward moisture flux consistent with the other moisture modes. But the MGO is not just exporting moisture through the poles. The MGO is also exporting motion, we can say, in all directions, zonal direction, meridional direction, weakening not just the Hadley cell circulation. In this case, the MGO also weakens this Walker cell circulation. Perhaps we can better explain what is the role of this moisture modes in the general circulation by using this schematic. This is the schematic of the ITCZ and the Hadley cell, in this case represented by this overturning circulation with more moisture, more precipitation over this region, and less moisture and less precipitation over this region. So this is the equatorial region, and this could be considered the high latitudes. So, which means there is a moisture gradient basically in this direction. The hypothesis is based in many other previous studies, is that the Hadley cell always want to step in the moisture gradient, always want to keep this moisture gradient as observed here. They want to have like a more organized ITCZ. But in the opposite, you have these unstable eddies driven by our moisture mode that basically doing the opposite. They are transporting moisture from this region of high moisture to the higher latitudes. In fact, acting to flatten the moisture gradient or trying to deorganize the ITCZ. So of course, the same happened with the Madden-Julian oscillation, but in the zonal direction. Of course, tropical eddies can cause the ITCZ to breaking down. This is, for instance, from orchestra. This is the maps from orchestra field campaign. The first row basically represent the total column water vapor, and the second one represent the precipitation. And this part of the figure is without wave
activity. And you will basically see a really well organized ITCZ in the total column water vapor, also in the precipitation. You can see, well, not really well organized, but you can distinguish where the ITCZ is observed over the Atlantic region. But when you have the passage of this tropical depression system over the Atlantic region, you basically deorganize the ITCZ. You don't have more really organized as was observed here when you don't have the wave activity. So if you generate like an index that measures this organization, you can also discover some interesting things. So for instance, here, this is the time series that describes the organization of the ITCZ, well, in this case, calculated for the Atlantic region. So the peaks here basically represent organized and less organized processes. And if you calculate the spectral peaks associated with this index that describes organization of the Atlantic region, you will identify some important peaks here. The first one is like a peak identified from 5 to 10 days, and that in fact correspond to the synoptic scale, that in fact, in this case, correspond to the TD-like disturbances. But the organization not just happen in this scale. You can also identify a second peak here in the sub-monthly time scale, that in fact other waves also doing the same role. So we can, for instance, attribute to the Rossby waves. Well, Madden-Julian oscillation in the season time scale, you can identify a peak here, but it's not significant according to our analysis, but this one is calculated over the Atlantic region. So over the Atlantic region, the Madden-Julian oscillation basically doesn't show strong activity over this domain. Just to try to summarize and understand a little bit better what the moisture modes are doing, we can do analogous analysis that baroclinic waves do in the mid-latitudes. So baroclinic wave or extratropical cyclones exist because temperature gradient over the mid-latitudes. We know this basically exists in the both hemispheres because the temperature gradient. But the same happens with our moisture mode. Our moisture mode, as shown at the beginning, exists because you have moisture gradient, which is causing the instability for these kind of disturbances. We also mentioned that the main function of this baroclinic wave in the mid-latitudes is to transport moisture and temperature to the higher latitudes to the lower latitudes. And the same happened with our moisture modes. Our moisture modes are exporting moisture from this region of high content of moisture to the higher latitudes. And this is perhaps the main role of these disturbances. As I mentioned at the beginning, well, in this case, the baroclinic wave disturbances weakens the jet stream, but the same happened with our moisture mode. The moisture mode basically weakened the Hadley sail, and well, if you're analyzing the Madden-Julian oscillation, also weakened the vehicle circulation. Okay, let's go with the main takeaways, the main conclusion. If you go back to our first question, we basically say the moisture mode exists or not over the tropics. We used some criteria and we demonstrated that the quadro Rossby waves and TD waves are the moisture modes, and moisture modes in the whole tropical domain. Madden-Julian oscillation also satisfies some conditions to be considered moisture mode, but these two waves are the waves that really satisfy the all condition to be considered moisture modes. Where are these waves are most common? I showed previously, this moisture mode basically occur in regions of a strong horizontal moisture gradient. They are not active where the cold moisture is maximum. So the gradient, the moisture gradient is more important that cause the instability for these disturbances. So we also demonstrated that the process that really controls the growth and propagation of this moisture mode is the horizontal moisture advection. So this is an important
characteristic of these disturbances. And finally, we can say what the moisture modes are doing. We can say that moisture modes basically are stirring the tropics. This is the main references used in this talk. You can access to all these papers by this QR code. If you can access it, just send me an email. I can share with you if you're interested to read our work. Okay, I think that's it. I'm now ready for a question.
Thanks a lot, Victor, for the very nice talk. I think we have plenty of time for questions. Yeah, I see 2 hands already.
Thanks, Victor. That was very nice. This is Marty Singh from Monash University.
I'm trying to.
Oh,
yeah.
You were talking at the end about this kind of interaction between the moisture modes and the Hadley cell, and suggesting that the reduction of the moisture gradient by the moisture modes weakens the Hadley cell. I guess that they also potentially have a momentum transport, especially sort of Rossby wave types, and they would, to the extent that they suck momentum out of the subtropics, they would accelerate the Hadley cell. Do you have any comment on how to sort of think about the different effects on the moistatic energy budget and the momentum budget?
Yeah, of course. Not just, well, here I demonstrated that TD is one player that do that. But of course, Rossby waves, I guess Adrian Trumpicus made like a clear analysis by using Rossby waves over the Indian Ocean or Western Pacific, I guess, where they also demonstrated that Rossby wave, in fact, do almost the same role, right? And trying to destabilize the Hadley cell circulation. But there is a very important thing here that maybe the eddies caused by these disturbances, you can think that compared to the Hadley cell, they are not super strong. They, of course, the Hadley cell is the primary energy exported in the tropical domain. But these disturbances actually, despite it's not too strong, also playing the same role in like energy transport in the Hadley cell circulation. So I'm not expecting like strong energy associated to these eddies. So that can be associated with TD or Rossby waves disturbances.
Right. But I guess, do they do anything to the momentum budget as well?
Yeah.
Thanks.
Hello. Yeah. So I had just one question that in some of your slides, you mentioned that horizontal advection is kind of proportional to the precipitation. I mean, dot item, that's basically precipitation variability. And later you said that the eddy kind of destabilizes the Hadley cell. So what do you think would be the implication of stronger eddies on the precipitation variability? Should it dampen it or should it enhance it? I mean, depending on if we think of a, let's say, northward propagating modes instead of westward, where the over Indian region, the gradients are kind of weak for moistures.
I didn't understand the last part of your question. Could you please repeat?
Yeah, sure. So I mean that if you look into the northward propagating BSISO mode, at least for over Indian region, the horizontal gradients of moistures are a bit kind of weak when you have the active phase of the BSIS, like you have a lot of moisture on the entirety of the subcontinent. So do you think eddies would kind of enhance or dampen the variability depending on that context?
Yeah, definitely. Of course, if you go to the Indian region, of course, the interseasonal variability is basically the same mechanism. The horizontal advection basically played a role in the organization. So you can say, at least for the slow propagation disturbances, you can say the horizontal advection. We found that the horizontal advection basically played a role in organizing moisture, which is proportional to the organization of precipitation.
Okay, yeah, thank you.
Hi, Victor. This is Rajat. Very nice talk. I had a couple of questions. First one is, you showed that the moisture gradients are essential for the moisture modes. do you know what sets up these background moisture gradients?
Sorry, what did you say?
What sets up these background moisture gradients that are essential for moisture modes?
What do you mean with sets?
So what controls these moisture gradients?
Well, so we're basically saying that the moisture gradient, we can do the same, or we can think in the same way in the temperature gradient in the mid latitudes. We can basically, if you think there is like a competition with the Hadley sail that is important dry air from the region trying to keep this moisture gradient, and the opposite you have this system that are doing the opposite, like exporting moisture through this region, and it's like a competition, right? You have a Hadley sail that's keeping the ITCZ really organized, and in the opposite you have these these disturbances, these rotational disturbances like Rossby waves and TTE and MGO that can basically try to flatten this gradient, the main gradient, moisture gradient.
Okay, another one is you showed some results from, I think, orchestra field campaign, and you said there was, if I remember it correctly, there was these moisture modes which were breaking down the ITCZ.
Yeah.
How different is that from the Schubert and Ferreira kind of thinking, where they have these barotropic instabilities that flux out some of these ITCZ breakdown into eddies? I think it goes back to Martin's question of how do we think about momentum balances and these moisture modes? Do you have a comment on that?
Yeah, we're still trying to explore that, at least over this region. Of course, if you go to the African region, not just temperature gradient matter, right? I'm sorry, not just moisture gradient matter. So over this region also, temperature gradient is also important for that cause instability on these kind of disturbances. So the general solution, I guess, for all these disturbances is a little bit complex. But the MBI, the moisture gradient, is just a part of this instability in the momentum equation. So we're still working on that, and we're trying to have like a general solution for that. But at least for the oceanic tropical depression system, I guess is the same mechanism.
Yeah. Thanks. The lady in the back, yes.
Hello.
Yep.
So I have a question from your introductory slides. So where you showed the Wheeler-Kilaris spectra. So I observed that overall we can see n equal to 1 westward inertial gravity waves, but the spectra is completely absent over the eastward wave numbers. So is it something systematic, like eastward inertial gravity waves are not at all observed, or is it regarding the data?
I guess it's regarding the data, and I guess was calculated regionally. So I guess in the Wheeler-Kilaris diagram is calculating the whole tropics, but if you do a more regional analysis, this can change, of course. It will depend where the wave is calculated. Yeah, definitely.
Okay.
Or the spectrum is calculated, sorry.
Okay, thank you.
Victor, this is Vishal from IIT Bombay. This is much more of a clarificatory kind of question. I was thinking about existence versus modulation of existing waves. So in terms of moisture mode, as you showed, N mode is a critical parameter, and only the Rossby waves and tropical depressions kind of really satisfy this criteria. So I was thinking, are you saying that, are you making much more statement about modulation of existing dry waves or existence of new waves which would otherwise kind of not exist?
Yeah, in this case, the N mode, that works at the same way to the criteria, but
You're basically saying that MGO, so the phase speed is basically taking a role, right? So which means as a slow propagate your wave, you have more time to eliminate temperature fluctuation and the WTG to come true, right? The dominant role. So
Sure.
this is basically the N mode is telling you.
Sure. But I mean, okay, maybe I'll ask as a kind of Rossby waves we get from dry theory. And we now see that they are the waves which satisfy N mode criteria in kind of the best way. So I was wondering, is moisture just modulating dry theory or yeah, that's my direction of question.
Yeah, of course. Yeah, you're saying that in the dry theory, the Rossby wave exists, right? But
Yeah.
if you
Which
want
features
to
of observed Rossby wave we cannot explain using dry theory, and we need really moisture on top.
Yeah, I mean, for instance, I guess Rossby waves is it's a special wave because even the structure in the observation looks like that which was predicted by the theory. But for instance, if you want to explain the slow propagation disturbances, you will need, for instance, an equivalent depth, which is like a non realistic value to explain the slow propagation of these disturbances. So the dry theory can explain a part of the characteristic of Rossby waves, but it is not explaining the whole features. For instance, the slow propagation of these disturbances. So you need to include moisture as a prognostic equation to have like a whole panorama of what's going on with these kind of disturbances. Yeah. And
Sure.
actually, Rossby waves and TD, if you work and you do the derivation, looks like both are the same family. Just an MGO as well. There are some works that basically mention that the MGO is a Rossby wave which is propagating in the opposite direction. So which makes some sense, I guess, from this point of view, from the moisture point of view.
Sure, sure.
Yeah.
And my second and last question is much more kind of naive question, actually. Can you give us some intuition about, so for gravity waves, either inertial gravity waves or just gravity waves, I can always think that gravity is a restoring force. For Rossby waves, I usually think that Coriolis or angular momentum conservation as the restoring force, trying to do mass adjustment. In case of moisture mode, how to kind of go about this sort of a thinking? Yeah.
So yeah, this is, yeah, I never think about that in this. Yeah, I don't know how to do like the analogous analysis, the dry wave for in case of the momentum. Yeah.
Sure. I understand. This is still kind of developing theory.
Still
so
developing,
maybe
course.
I must. Yeah, sure. Thanks a lot.
Yeah, thanks
are
for
there
the
any
question.
other questions? Yeah.
Hi, Victor. It's Spencer Hill. Great talk. I stepped
Hey,
out for just
Spencer.
a moment, so extremely sorry if this has already been covered.
Yeah. It's midnight here.
So you showed a plot of the spectrum related to the organization metric for the Atlantic ITCZ, right? And what I noticed was this red noise background and the 95% confidence sort of level above that. The peaks you mentioned stood above it, but so did essentially everything at high enough frequencies. And so it almost, yeah, I was just wondering what's going on there. Is that the red background noise spectrum you guys have? Are you sure it's the right one? Or if it's indeed right, like what is that significant stuff happening at these high frequencies?
Do you say for the higher frequencies?
Yeah, exactly. It was like the MJO and the low frequency stuff were the only ones below the background, right?
Yeah, but this is because in the Atlantic region, we did the same calculation over other regions, for instance, Western Pacific and Indian Ocean. Basically, the strongest peak is observed in the Madden-Julian spectrum, Rossby wave spectrum.
But in the Atlantic region, I guess because MGO is not like really active, this is maybe why it's not really like significant over this domain.
Yeah, that makes sense. But so then what about the high frequency part?
At the high frequency, I guess this is like I need to check that one because looks like it's like the red noise a little bit weird for the higher frequencies. But in fact, higher frequency 2D variability or diurnal variability maybe is also in these peaks. But I'm trying to basically to highlight it, the other instruments like TD and Rossby and Madden-Julian oscillation. The discussing this organization of the ITCZ. Yeah, but definitely I need to go and check in detail what's going on in the higher frequencies.
Cool, thanks. And then one more of that. So I don't know if Angel mentioned to you, I shared with him some results from Haochan. When we've done these co-spectra of the meridional MSE flux at 850 in era 5, and on either side of the ITCZ, no matter across all wavelengths, all wave numbers and frequencies, the flux is poleward, right? So on north of the ITCZ, there's northward, and south of the ITCZ, it's southward. And that's just like across the whole spectrum. There's not a single exception. And so I'm trying to reconcile you guys' really compelling work about the moisture mode sort of predominance throughout the deep tropics and that part of the story. So that's not really a coherent question, but just any thoughts on that?
Oh yeah, that is like I don't know if like the whole spectrum corresponds to this moisture mode. Maybe there are other things that is going on, right? As you maybe mentioned, moisture mode is just a part of this. And I don't know what exactly you found with doing that analysis, but moisture mode definitely is not the whole. There are other things going on. I guess that is my thought.
If you stick around to I'll show one slide for you and everyone about this to start my next talk, okay?
Okay, cool. That was super cool. It just, that was super cool. You are next, right?
Yeah. Let's thank Victor once again for his nice talk.